Okay, great. If you have questions, put them in the chat or sorry, not the chat, but the Q&A section. And we'll try to answer them on Twitter after the show. And our Twitter handle is @CarletonScience. Okay, and I think somebody's going to be able to type that in here in the Q&A for us. And let's get started. Okay. Good morning, everybody, and welcome to the 14th Annual Carleton University Chemistry Magic Show. Okay, so I hope you liked that first demonstration. That's one we call flash paper. Okay, and what that is, I can show it to you up here on the camera. I can show you a little piece. Okay, so this is just like streamers you would put up at a birthday party. Okay, but what we did was we actually reacted them with some extra chemicals that instead of making them resistant to burning, which is what they are when we buy them at the store, the bag actually said flame resistant, so it's actually hard to light it on fire. I didn't save any because I didn't have much, but otherwise I'd show you. And it won't actually burn unless we're holding a flame right to it. But now, with this, you can see there's no smoke, no ash, nothing left. Okay, now, let me guess. You want to see that again, but maybe a little bit more. Okay, why not? Okay, maybe we can turn the lights off again. And here we go. Woo! And that's why we get the fire alarms turned off. Okay. Yeah, we did.
I think we got them turned off.
We did. Okay, what do you got for us, Bob? By the way, this is Bob Blow It Up Burke.
I like blowing things up and setting them on fire. You'll see lots of that today. But the first demonstration I'm going to do does not involve blowing things up or fire. I need Jeff's help for this. I want you to watch these 5 beakers across the front of the table here. And when I say go, we're going to dump these in. 3, 2, 1, go. Now don't take your eyes off these 5 beakers, not even for a second. Watch very carefully. Well, we'll put that one there. 2. Sometimes they don't go right away. Sometimes they go if you turn around and you don't watch them. There they go.
All right.
So that's called a clock reaction. And those went at different times because we used different concentrations of the chemicals in these solutions. So the lower the concentration is, the slower the reaction goes.
Okay, that's pretty cool, Bob. But I have another one for you.
Let's
okay?
see.
All right. So this is another clock reaction. Okay. So we're going to do a few demonstrations about the big holiday coming up. What's that? Everybody yell it out if you want to. It's okay.
Easter.
We can't hear you.
No, Christmas.
Okay. Well, the last holiday we had was what? Halloween. Okay, so what are the colors for Halloween? Orange and black. So I'm going to do a clock reaction that makes orange and black.
I don't believe it. Nothing's happening, Jeff. Hop. And whoomp.
All right,
Awesome.
There we go.
The Halloween reaction.
Halloween reaction.
One of our favorites.
You can top that, Bob?
Well, I'm going to try my best to top that. I've got another clock reaction here in this beaker, which has a stirrer in it. See that little magnetic bar is turning because of the motor that's underneath it there. I'm going to add these 2 solutions at the same time. And I don't want you to take your eye off it for a second. So it's a deep yellow color. Whoop! Okay, but don't take your eye off it. We're not done yet. Don't go away. Keep watching, keep watching. Clears up. It's not over yet. This is called an oscillating clock reaction. And this will oscillate blue to colorless for about 15 minutes, something like that. It's actually quite a complex set of reactions involving many chemicals. It took a couple of hours to make this, to make these solutions up, but we think it's worth it.
Don't look at Jared's, look at mine.
And gradually it'll get slower, but it'll keep going. It'll probably oscillate about 40 or 50 times, something like that. So the chemistry is not too dissimilar from the first one that I did. It's quite different from the mercury chloride, the Halloween reaction. We call that the oscillating clock. While that's oscillating, I'm going to show you something else. So on this ring stand, you can see 3 pieces of paper, and you can see a bit of a dark spot in the middle of each one. That's a compound called nitrogen triiodide. So I'll write it on the board here for all you chemists, Ni3. And what nitrogen triiodide likes to do is fall apart into nitrogen and iodine. And when it does so quite explosively. So you're going to hear a bit of a pop, and that's because of the nitrogen and the iodine gas being released. And you're also going to see a little bit of a purple gas. That's the iodine gas that's being released. Now, all I'm going to do to make this go is to touch it. And I could touch it with a feather, but I don't have a feather here. I'm going to touch the bottom one, but I want you to see that the other ones also go because of the shock wave that's created. So when one goes bang, they're all going to go bang. So you ready? Lean forward in your chairs. Look carefully. Watch carefully. Listen carefully. Whoop. There we go. Now this one blew. See the purple gas here? That's iodine gas. So that's the iodine coming off the Ni3. That big bang is because the nitrogen is a gas and the iodine is a gas, and they occupy more volume than the solid did. So the first one blew, and that created a shock wave which blew the second one, and likewise for the third one. So that's called nitrogen triiodide. Cool, eh?
Okay. Whew, my ears are still ringing from that one.
Yeah.
All right. I want to take a minute to give a shout out to some schools that are joining us. If you're watching, we've got 441 participants here. Okay, so we've got close to 10,000 people watching this show right now. That is amazing. Thank you all for coming. So we want to give a special shout out to people in the Ashton area, Markham, Petawawa, Barhaven, Manotick, Orleans, Morrisburg, Richmond, Oxford Mills, and Winchester, just around here. Okay, and I'll bring up more later. Now, let's make some slime. Okay, so if we're going to make some slime, well, I mean, it's got to be green like boogers, right? So there we go. We'll put a little bit, some green food coloring in there. Okay, and what I have here is a solution of borax, which is a type of laundry detergent, and I have some wood glue. Okay, and I'm just going to mix these together. This is the kind of thing you can do at home or at school. Okay, you might have to do some experiments with the particular glue you have and if you need to dilute it with water and how much borax you add to make it. But that's part of being a scientist, is we're not always sure how much of different things we need to add to make something work, even if we think it's going to work. And now you can see getting lots of good gooey slime. All right, so now I'm going to add a little more borax.
Looks like snot.
Yeah, looks like stuff my daughter's been producing with her cold, but she's not on here today. And that one daughter, she's at daycare. But yeah. All right, there's some good goopy slime. All right, now I might even have a little too much borax, so let's mix it up again and we'll add a little more glue. Okay, look at that.
Pretty gross.
That's pretty gross. Achoo! I can take that off and You can see it's pretty gooey stuff. Okay, so that's some slime. You can try that at home or at school. Okay, what do you got, Bob? What's up next?
I have what's called sodium and water. Here, you can wipe the slime off your fingers.
Oh, thank you.
But I'd first like to point out that my clock reaction is still going, Jeff.
Okay, yeah, you win.
Oh, maybe it's stopped now. But a moment ago, it was still going. All right, Jamie, if you can switch to the overhead. What I'm going to show you here is sodium metal. Now, you see it says Na on the top of the jar here. That's the chemical symbol for sodium. And sodium is a metal, kind of like iron or copper or something, but it's quite a soft metal. So I'm going to take this and I'm going to cut off a little piece here, and you're going to see that I can cut it with a knife. It's kind of like hard butter. That's about how hard it is. Now, that's a fairly big piece, so I'm going to cut that in half. But you can see that nice shiny surface there. That's the bare sodium metal. The outside of this is covered in an oxide and an oil. What I want to do is expose this sodium to water, because sodium is a very reactive metal. If I put a piece of metal in water, a piece of iron for instance, it's going to take a long time to oxidize. These forceps have oxidized over the years. But if I put a piece of sodium in water, it oxidizes just like that. And this is why the firemen really want to know what's in our labs, because if there's a fire and they come in and they spray water on everything and those things react with water, we could have a problem. So I'm going to put this big chunk back in the bottle where it's safe here. I move the bottle away. And in the cylinder, I've got maybe 5 centimeters of water. I'm going to take a piece of sodium and drop it in there. Now, if I dropped a piece of iron like this in there, not much would happen. It would rust, but it would take days or weeks. A piece of sodium, that's different. I'll just back up a little bit here. It's hissing. There we go. That's what I'm talking about. Just make sure we didn't set the ceiling on fire. No, I think we're good. So that's an explosive reaction because the sodium reacts with water. Water contains hydrogen, so the reaction releases hydrogen gas. And then the fact that the reaction releases a bit of heat, that causes the hydrogen to explode. And I think I've stained the ceiling. I'm probably going to hear from the Dean of Science about that one. But what do you think, Jeff? Should I do another one?
Sure.
Oh, I hear yes from the booth. Okay. I've got this piece left over. It's not like I can do something with it. Let's put another one in.
Hang on a sec. You might need some more air in there.
Oh, yeah, that's a good idea. There has to be enough air to make the hydrogen explode. And the reaction blows some of the air out of there. So Jeff will provide the air. Good thinking, Jeff. Good thing the smoke alarms are off.
Yep. Good thing I'm a windbag, too.
Oh, that's true. I wasn't going to say that, but.
Okay.
I'm also going to show you that the solution turns basic. So for those of you who are chemists, you'll see this pink color when I add an acid-base indicator. That's because the reaction also releases a base. So now the second piece of sodium. It's hissing. It's smoking. It's flaming. Sometimes it does that. Sometimes it does that. Isn't that just the coolest thing? It's a piece of metal reacting with water. Ha. Don't do this at home. What's next, Jeff?
Okay. Now we're going to have a little bit of fun. Okay. Here's a challenge for you. All right. I'm going to put this in here. And now, you ever wondered how diapers work?
No.
No? You're just glad they work?
I don't think about diapers.
No? Come on, you got grandkids. You can't.
Yeah, I don't change my grandson's diapers.
Okay. I'm going to put a little bit in there. Okay, and now put some water in here. Try to remember which one had the water in it. Okay. So which one is it? Is it the one here on the right?
I think so. Oh,
No. Is it the one in the middle?
gotta be. Oh, well, now we know which one it is. Oh, come on. What did you do?
Well, what I did was forget to bring an extra beaker.
I'll give you a beaker.
Here we go. I got one. All right. Now I'll show you what that's like. In a beaker. So here I have a polymer, which is a very, very long chain of molecules. Okay, and this polymer likes water. Okay, we say it's very hydrophilic. Okay, and so when I add that, what it does is it soaks up all the water really fast. And this is what's inside diapers. So when a baby pees in there, very, very quickly you can see that it soaks up all the water and forms a solid. So that's called a super absorbent polymer. And now it's almost like, thickened oatmeal or something like that. It has that sort of consistency. Okay, so that's a super absorbent polymer. All right, what do we have now?
Maybe the sodium acetate?
Okay, right. I got mixed up. Okay. Now, this is a fun one. Okay, so sodium acetate. This is what's on salt and vinegar chips. Okay, it's also a very interesting salt. Okay, so it has the sodium part there tastes like salt. Okay, and the acetate part tastes like vinegar. So that's why it's salt, and we can use this on salt and vinegar chips, and they don't get soggy like if we'd actually put vinegar on them. Now, because vinegar is a liquid. Okay, it also has a very interesting property called supersaturation. So we can dissolve it in water, and there's more in there than, in theory, it should really be able to dissolve. Okay, and if we add just the tiniest bit more, okay, I have a little bit here. You can see it all comes crashing out of solution. It's kind of like the last demonstration we did, right? Okay, so that's called supersaturation. And now I can take this and I can heat it back up and use it again for our next show this afternoon. Okay? All right, now I'm going to mess with our cameraman here and turn down the lights a little bit. They weren't expecting me to do that. Okay? And I'm going to show this in a different way.
Ready?
Yep. And now I've got some here that kind of glows in the dark. And if I pour it out onto a little bit of sodium acetate in the pan, you can see it grow and glow. Okay, so that's a phenomenon called supersaturation. It's also how we get frost on windshields. In the wintertime, the air becomes supersaturated with air and then forms ice very quickly on our cars. Okay,
Good one.
so that's more sodium. Do we have any more sodium demos, Bob?
I have a sodium demonstration right now. When the sodium in its tube blew up, especially the second one, you saw a bit of a yellow flame. And that yellow color tells us that sodium is present. It's the same color you see in sodium streetlights, which have that orangey yellowish glow. And so I want to show you that wherever there's sodium, we can tell that it's there because of that color. So I've got another demonstration here we like to call the electric pickle. If you could pull up the lights for a moment, I'll just show people how this works. What we have here is a jar of Strub's kosher pickles that we've had for I would say 7 or 8 years now, unrefrigerated. They don't smell very nice, but they're amazingly still well preserved. I wouldn't eat one, but well, maybe if I was starving. And what I'm going to do is impale this pickle on these 2 forks. So I'm just going to push down like that. And we call this demonstration the electric pickle because we've now connected these 2 forks to a source of electrical power. And I'm going to turn up the power. Eventually I'm going to put about 120 volts between these 2 forks, and I want you to see what happens between those 2. If you could turn the light down, please. So the power's on, and I'll gradually turn it up here. I can see the pickle's starting to boil. There we go. Now that color is exactly the same color that you saw when the sodium exploded in that tube of water, because it's also sodium. Why is there sodium? I think you guys know, because pickles are made by submersing a cucumber in salt water, and salt water contains sodium chloride. So there's a lot of sodium in a pickle, and when the electricity excites the atoms, then they lose their energy, and they do so in the form of this yellow light. And that exact color of light tells us that it's sodium. So if you look at a fire in a fireplace, you're going to see that color because there's sodium everywhere, and the fire excites the sodium atoms the same way the electricity is doing here. And it's the same inside a streetlight. Streetlights don't contain pickles. They contain a little bit of sodium metal, but it's exactly the same element, and therefore you get the same color. So we call that the electric pickle. And it really stinks. Frying a pickle is not something you should do, I guess, unless it's been deep fried maybe and battered and deep fried. Between 2 forks at 120 volts, it's not the same meal. That's the electric pickle.
Okay.
Oh. There's still a bit of sodium, Ni3, nitrogen triiodide on the desk. Let's get rid of that.
Okay. And while Bob's setting up for his next demo, I want to just say hi to everybody that's joining us from Brooklyn, Mid-May, Smiths Falls, and Creemore. And a special shout out to Miss Anderson and Miss Kennedy's class at LaFair Elementary in Ottawa, and anybody watching from Glen Ogilvy here in Ottawa too. And for now, the last shout out I'll send is to a place where my mom used to live, and they, I think, are maybe our most northerly attendees this morning are groups from Moosonee and Kashechewan schools.
Good for you for being here.
Yeah, thanks for coming.
All right, now I'm going to show you something that's a little bit more related to physics than to chemistry, but there is a chemistry connection. This is a Geiger counter, and what this will do is detect radiation, so radioactivity. The way this works is we have a tube. So I'll take the cap off here. The tube is filled with gas, and if there's radiation nearby, the radiation will pass through this window and create electrons inside the tube, and the electrons are collected, and they're displayed on this meter here. As the needle moves up, it says there are more radioactive particles entering it. So I've got a small sample of uranium trioxide here. This is what would be produced at the Minehead in northern Ontario, northern Saskatchewan, and then shipped around the world to be refined into nuclear products. And so if I bring that up to here, maybe you can hear the buzzing, and you can see the needle moving up. And so the meter is counting those particles that are coming right through the glass, all the way out of this sample of uranium, through the glass, through the window in the tube, and registering on the meter. And what I also want to show you is that if you want to protect yourself from radiation, there's 2 things you can do. You can move away from it. The closer, you're going to be exposed to more. If you move away, you're exposed to less. The other thing you can do is put some mass, of any type of mass, between you and that source. So I'll put that there, and then I'll find something. What do we have here that I can put in between the 2 of them? Let's see, even just a bottle containing some liquid. So you can hear the clicking there. Now if I put this in between, it almost stops. Let me move that over so you can see that in the camera. So if you put something between you and the source, you protect yourself from radiation. And that's why in the dentist's office, the technician runs out of the room and stands behind a wall that contains lead. And
they also put a blanket on you.
You can move away. That's right. They put a blanket over you so that most of you is not exposed to the radiation. So either move away and or put some mass between you and the source, and you'll be safe from that radiation. So this is how we protect ourselves from radiation. Now, this is uranium trioxide. It's also a chemical, so it has chemical properties that probably are more dangerous than its radioactive properties. It contains what we call a heavy metal. That's the uranium itself. And so chemical toxicity is at least as important to our safety as is the radiation from this sample. So that's a portable Geiger counter and some uranium trioxide.
Okay, and now I want to send out a few more shout outs to friends at St. Emily's School in Ottawa, St. John Bosco School in Barry's Bay. We've got a bunch of classes joining us from Walkerton, and Walter Zadow Public School in Arnprior, a couple schools in Canada, Knoxdale Public School, Ottawa Virtual Schools are joining us, the Ottawa Jewish Community School. Bonjour to those tuning in this morning from Pierre Trudeau School over in Gatineau. Good morning, later in the morning to the folks out at Sacred Heart School in Halifax. You get the prize for being the school farthest east this morning. And Sergeant Park School in Winnipeg, you get the prize for being the furthest west that's actually joining us live. And then we have another school out in Kelowna who's actually going to be watching the recording because they probably didn't want to go to school for 6:30 a.m. just to see the show.
And there was another Sacred Heart there, Sacré-Cœur from Bourget.
Yeah.
Welcome.
So, yeah, this is a great turnout. And now Bob and I are going to have a bad breath contest. Ready, Bob?
I'm ready. Got to pull my mask down. Notice that this is pink.
Mine's blue.
Your breath is obviously worse than mine.
Hey, wait a minute, it's not blue anymore. I broke it. Oh, I fixed it. It's blue again. Because I get it? Because I blew into it?
You blew it?
Yeah.
I think I'm going to pass out.
Oh. Hey, wait a second. It's changing back again. Oh.
So you see mine is gradually turning from pink to clear, and that's because of the carbon dioxide in my breath. That's an acid compound. So that's turning the solution from basic, which I made it before, to acid.
And mine actually contains a dye called methylene blue, which turns blue, but it can be reduced to a colorless form. It can be converted to a colorless form, and I put some stuff in the water there with it to react with it to make it colorless. And now it reacts not with carbon dioxide that I'm blowing out, but with extra oxygen that I'm blowing out, and that's what turns it blue.
Whoop. Okay, it's finally turned almost clear, but I want to show you that I can turn this back to what it was, which was a basic solution. Right now it's acidic because of the CO2 from my breath, but I can turn it back to a basic solution by pouring some base in it, and it goes back to a dark pink color. So that's a reversible reaction. That'll go in either direction. If I add acid, it'll go clear. So with my breath, it took a bit of time. How about I add some stronger acid here? You can see the color will change back to clear pretty much instantly. There. And if I added a strong base, it would turn pink again. So we call that a reversible reaction. It'll go backwards and forwards as many times as you want it to.
And this one I can also get it to react with oxygen in the air just by shaking it. And there's enough oxygen inside the flask to make it blue, and it'll keep turning back and forth as long as I keep shaking it. And the chemical that it's reacting with doesn't run out in the solution. Okay. All right. Now, with the holidays coming up, we figured we'd do a couple sort of Christmas-themed demonstrations for you. So earlier we talked about what colors we use for Halloween. We talked about orange and black. If we're going to talk about Christmas, we're probably looking at silver, red, and green. Okay, so I'm going to show you a silver, red, and green demonstration. So in this flask here, you can see I have a silver liquid. And now on top of that, or mix in with that, I'm going to put a green liquid. And on top of that, I'm going to put in with them a red liquid. Okay, so if you notice there, I've got 3 layers. And now watch this. If you think I mix it up, they'll all mix together and we'll probably get some sort of brownie color, but watch this. Shaky, shaky, shaky. Give it a second. And there we go. We've got our red, green, and silver back again. And it looks like we've got a little octopus hanging down from the red into the green. Okay. So this is what we call a triphasic mixture. There's 3 different phases here that don't mix. So the top layer here, we'll call that a phase. Okay, this is an oil-like layer. So it's like if you're when we're cooking, right? We might put some oil in the boiling water when we make pasta. Helps prevent the pasta from sticking together. So this is an oil-like layer that sits on top. It doesn't mix with the layer below, which is water. And I put in something in there to make it green. I actually put 2 things in, some food coloring and a special salt. And then on the bottom here, I actually have mercury, the element. So it's silver, it's a metal, it's liquid. It's very unusual in that it's liquid because elements are just only atoms, they're not molecules. And so this element here is one of only 2 that's a liquid at room temperature. Okay, and it's the only metal that's liquid at room temperature. Okay, so that's one of our favorite Christmas demos. Okay, we can shake it up again and 3 layers. And by the way, mercury is also very dense. So if we have a jar of it, okay, let me see, where did I put it? There it is. I can show you a big jar of mercury. And I wish I had a scale here so I could explain how much it weighs. But right there, that's about 300 milliliters. And that probably weighs about 3 kilograms. So that's, it's one of these things when you go and pick it up, you're like, wow, that's so heavy. It's like your brain just goes, that amount should not weigh that much. It's worse than trying to pick up a brick. Okay, what do you got for us, Bob?
Okay, another Christmas demonstration. I'm going to make one of the world's biggest Christmas ornaments. This is full of hot water right now, which I'm going to empty. So I've got a bucket here, and I'll get rid of the hot water. And what we're going to do is a reaction which is going to cause the inside of this flask to become coated in silver like a mirror. And I'll explain the chemistry as soon as I get the water emptied out of here. All right, so the water's out, the flask is nice and hot. I'm going to put a solution in which contains a bit of sugar. 10, 20, 30, 40, 50, 60 milliliters. Looks about right. And I'm going to add another solution which contains silver, but you'll notice that you don't see any silver metal here. The silver is dissolved in solution. We call it silver ions. So I'll add this to here. And a reaction should happen between the silver and the sugar. So the silver will get reduced to silver metal, and the sugar, as we say, gets oxidized. But the important thing here is that the silver becomes silver metal. So you can see that things are starting to happen on the wall of this flask. And gradually the silver ions will come out of solution and become silver metal, and the solution will become oxidized. It'll turn into carbon dioxide and water, and you won't be able to see that. But what we're going to do here is make the world's biggest, well, maybe not the biggest in the world, but we're going to make a pretty nice looking Christmas ornament. Come on over here, Jeff, because I want people to see us in the reflection of this bulb here. So you can see that now it's nice and shiny. It's not clear anymore. What do you think of that? We could hang that on a tree once we empty out the toxic contents inside and wash it a little bit.
Would we call that a chemistry?
Oh, a chemistry. Oh, my partner here is so... Got another one of his jokes. Anyway, that's the reduction of silver ion to silver metal to make a giant Christmas ornament. And I'll wash this out and I'll put a little bit of nitric acid in and it will dissolve the silver again, and then we can do the reaction again with some fresh reagents. But that's a nice big Christmas silver ball.
In the old days, that's how they would make those silver ones.
That's
now
right.
it's mostly aluminum.
Mostly aluminum. This is how they used to make mirrors too. They would reduce silver onto the back of a piece of glass.
Okay, maybe Bob can get the lights while I get this next demo ready here. So another thing that we have a lot of around this time are candles. So I've got a little candle right here. Okay.
Pretty ordinary looking candle.
Yeah, pretty ordinary looking candle. Okay.
Oh, come on, Jeff. You can't eat a candle?
Yummy candle.
Gross. Who eats candles?
I do. They're delicious. So, this is one you could try at home with Mom and Dad's help. Okay? If you have what we have here. So maybe I'll turn the light back on and I'll show you how it's done. So, what's it actually made out of? Well, the bottom part's a banana. The top part here is a pecan. It's a kind of nut. And so if you have a nut allergy, well, don't do this. Okay? And now what I'm going to do is I'm going to light it, and the nut will actually catch fire because nuts contain a lot of oil. Enough oil that it will actually keep burning for a minute or two. And now, all I have to do, blow out the candle and take a big bite with lots of banana so I don't burn my tongue.
Roasted pecan.
Okay. Best tasting demo all day. Healthy too.
All right. How about we blow something up? Oh, I can hear 10,000 people going, yeah, blow something up, Bob. What I have here is a copper cylinder. It's got about a 2 centimeter hole at the bottom and maybe a 2 millimeter hole at the top. That's hollow. It's made out of copper. What I'm going to do is fill this cylinder with hydrogen gas. So we call this demonstration the hydrogen bomb. I'll show you here what that looks like. Turn up the gas a little bit. So that fills this up. I can feel hydrogen coming out the top, and that displaces the air from the cylinder. So the cylinder should now be full of hydrogen, and there shouldn't be any air in it. Okay? Go ahead. I'll put my finger over the top because hydrogen's a very light gas, and it comes out the top. Could you bring me a flame of some description? Now, Jeff's going to light the top here. The hydrogen, being a light gas, is going to burn off the top. And if we hit the lights, then you'll see that there's a little flame at the top of this. So what's happening is that the hydrogen is burning off at the hole at the top, and that's drawing air into the bigger hole at the bottom. So gradually the mixture of hydrogen to oxygen is going down, or oxygen to hydrogen is going up. And eventually this gets to something called the lower explosive limit of hydrogen, which is just the right mixture of hydrogen and oxygen that an explosion occurs. Now what I want to do is show you that it makes some interesting sounds on the way. Let me go around the back. It's starting to make that sound already. Sounds like a bomb, doesn't it? Lean forward in your seats. Listen really carefully. That sound is getting lower and lower in tone. Oh! There we go. That was a good one. I can't hear a thing. I hope everybody enjoyed that one. It's much louder in the classroom than it is at home. Depends how much you had your volume turned up. But I hope it scared the heck out of you. That's called the hydrogen bomb. For obvious reasons. Oh, that just never gets old.
Oh, yeah, it never gets quiet either. Okay, and now we're going to have some fun with a black light. Okay, so this is something you can do at home if you have one. I have a couple of black light flashlights here. They're UV lights. Okay, and they kind of turn blue. Okay, and they can be used for checking and seeing if there are things you can't see when the regular lights are on. Okay, so sometimes you can see like lint on clothes and things like that. Okay, what I have here in this beaker is actually some laundry soap. Okay, so I'll just turn the lights on quickly, show you. See, it's blue like laundry soap. And now turn it back off. See, it glows. So if you've seen commercials for laundry soap, they'll say, gets your whites whiter and your colors brighter. Well, there's a chemical in here that actually takes UV light like this, so ultraviolet light we can't really see, and it absorbs it, and then it throws it back out in ways that we can see it, and so colors do actually look brighter. Okay? And one of the ways that this works in real life that's really helpful, Bob's trying it right now, are with things like highlighters. Okay, that's one of the reasons they look really bright. So let's try and take a look at that.
So I've written a few things on the back of this piece of paper in ordinary highlighters. And the highlighters contain inks, which are fluorescent, meaning that if we hold it up to an ultraviolet light, the light excites the molecules in the ink. And then when they de-excite, when they lose their energy, they do so by emitting light that you can see in the visible portion of the spectrum. So those are 3 different colors of fluorescent inks, but you'll see they all fluoresce at about the same color. So there's some science behind that, which I'm not going to go into here, but you can see how much they do fluoresce. If I take it away, you can still read it, but it's not nearly as striking.
And the last way we want to show you this phenomenon is with this is tonic water. So this is a bottle of tonic water I picked up at the grocery store. And if we put that under here, you can see it glows with a faint blue color. And that's from a substance in there called quinine, which used to be and is still sometimes used as a drug to treat a disease called malaria. And just to prove that this really is tonic water and something you can drink, here we go.
Oh, Jeff, geez.
Oh, man.
You a slob?
Oh,
what
yeah.
are you doing? Gonna get in trouble.
How do my teeth look?
Kind of greenish, actually.
Oh, man, that stuff tastes terrible, too. Ugh.
At least you won't get malaria.
Yeah, well, I have to drink about 30 liters a day to get enough to help with malaria. Okay. All right, and now we've got a related phenomenon called phosphorescence. So,
all right, so inside this bag, I do have 2 sheets of paper that have been treated with a phosphorescent substance. Now, phosphorescence is a little bit different because it persists, unlike the fluorescence. So phosphorescence is similar to the fluorescence that you saw, but it persists. And you've seen phosphorescence maybe in your TV remote control. Sometimes it has phosphorescent buttons, and they sort of charge up when it's light. Then if you turn the lights off, you can find your TV remote because they're still glowing. They continue to glow for some time. Now, what I'm going to do here is demonstrate with these two pieces of paper which have been treated with a phosphorescent chemical. And I have two laser pointers. One is red, and you can see that the red light doesn't do anything. It doesn't induce any phosphorescence on this compound. But the other one is blue, and blue light is more energetic than red light. The photons which come out of this laser pointer are higher energy, and they're capable of exciting the molecules in these phosphorescent molecules to a higher level. So watch what happens here. You can see I'm kind of jiggly. I must have had too much coffee this morning. But there it is. It's light fluorescence, but you can see that it persists. So the structure of the molecules is a little bit different. Note that they have to be excited, though, using a high energy photon like this blue light. The red light here doesn't do anything. The blue light is capable of exciting it. What's Jeff got here? Oh, he's got some big torches with UV light coming out of them, or blue light coming out of them, so he can excite that whole thing. So that's phosphorescence. And like I said, you've seen this probably in your TV remote control. The buttons have a phosphorescent chemical in them. Cool,
okay,
eh?
yeah. And now we're running out of time, so it's time for one more clock reaction.
Well, you can't beat the last one. I mean, mine cycled for
I'm
20
try.
minutes.
How about a clock reaction that glows?
I don't believe it.
All right, well, let's give it a try. Ready? 1, 2, 3.
Oh, look at that. Light coming out of a liquid. How could that possibly be?
So this is what's called a chemiluminescence reaction. So this is kind of what happens with glow sticks. Okay, this is a much faster process here. So you can see it took a little while for those to turn on for some of them, and we did that by changing the amount of different chemicals that are in the solutions. But and this reaction, instead of giving off energy as heat, it gives it off as light, which is not as common, but it does happen. So that's called chemiluminescence. Okay.
Keep going, my friend.
All right. Well, I think right now we've got 3 more demonstrations to do. Okay, and Bob's going to get started with one here called Thermite. And I'm going to give him a hand here.
So Thermite is one of my favorite demonstrations, because in this demonstration, we are going to make liquid iron in a matter of seconds. What we have inside the upper clay pot is a mixture of aluminum oxide, Al2O3, and very finely divided, iron oxide, Fe2O3, and very finely divided aluminum metal. Now they're mixed together, but they're not reacting. What we have to do is heat them up a little bit to make them react. So I'm going to take a fuse, let's call it, a party sparkler, and put it in there. And then I'm going to, where's the other torch, Jeff?
Here, I'll give you this one.
Okay.
You ready?
Yeah, you tell me when.
Go ahead.
Okay, well, I just like to move a few flammable things away here. What I'm going to do is use this torch to start the party sparkler. And then the very hot sparks from the party sparkler are going to start the thermite reaction. Shall I go?
Yeah, go ahead.
Okay, so here goes the party sparkler. Now, one of those sparks will fall into that mixture and start the thermite reaction. And if this works properly, you'll see something come out the bottom of the upper flower pot. And that something is liquid iron. We're going to make liquid iron in seconds here. There it goes. Now watch what comes out the bottom. There it is. That's liquid iron that just poured out the bottom of this. This is how they can weld railway rails together in the field. They can go out into the bush and they can put thermite above the ends of 2 railroad rails, and they can actually weld them together because that's such a hot mixture. Now I want to show you that that piece of liquid iron is still pretty darn hot. I can pick it up here and pull it out. It's still soft even. I can squeeze it with these tweezers. It's buried itself in the sand there. This is still quite pliable, kind of like soft glass. So isn't that amazing that a chemical reaction can release so much heat so quickly that it can melt iron? So that's called a thermite reaction. And mostly it's just fun to do, but it does have some practical applications in the field as well. These things will stay hot for probably half an hour. It'll take that long before I can dispose of them properly in the garbage. So that's called thermite. What do you got, Jeff?
Okay, so I have our second last demonstration here, and this is one that's a little bit related to fireworks. So there are three parts to fireworks. One is a metal salt that gets excited. That gives us the color. The other thing is a lift charge that causes the firework to go shooting up into the sky. And then there's the explosive charge, which makes the firework go pow. The chemical I'm using right here in this is potassium chlorate, which used to be used as part of an explosive charge. We don't use it anymore, and don't worry, this isn't going to explode, okay? But what I'm doing here is I'm liquefying it, and it's an oxidizing agent. So what it's going to do is it's going to break down this peanut M&M that's here in my hand, okay? Just like our body uses oxygen to digest our food. Okay, so watch what happens when I put this in. There's 13 calories in here, and that's not really easy to understand what that means. So I'm going to show you how much energy that is. Okay, so watch this. Okay, and this is a little smoky, that's why we're doing it inside this, what's called a portable fume hood here. Okay, here we go. So right now it's oxidizing the chocolate, that's about 700 degrees, and now it's going to start in on the peanut, which, like the pecan earlier, has a bunch of oil, so it's going to get a lot hotter, over 1,000 degrees. Okay, and yep, it's beeping at me here. Okay. So that's that one. Woo! That's one hot M&M. Okay, and our last one, well, how do you end any good chemistry show? How about a beeping fume hood? How about something that's actually like a firework? Okay, I just have to find the right bottles here.
What Jeff is trying to say is, let's light something on fire.
Yeah, let's light something on fire. There we go. All right. So I have three that I'm going to show you here. Okay, one should be red. One should be blue, which is actually really tough to do for fireworks. And one should be sort of a purpley color. Okay. So thanks everybody for coming. This has been fantastic. You've been a great audience.
Well, we think you have.
We think so anyway.
We can't see you or hear you, but we know you're out there.
We hope you had fun. We've had fun doing this for you. We hope you'll come back again. Okay, and here we go. Purple. How about red? Okay, and here we go with blue.
Oh, that's a good
one. Okay, folks, thanks a lot. That's our show. Hopefully we'll see you again next year and maybe in person.
Oh, wrong button. We'll do this again next year. We have other shows running during the year as well, so keep your eyes open for them if you're in the Ottawa area. Have a good day, everybody. Have a good holiday. I hope you all become chemists one day.